Okay, so this time I'm going to be talking about sequence modeling and a tool for doing sequence modeling, recurrent neural networks. And this is kind of core to everything we do in NLP. So I'm going to talk first about like the overall framework of sequence modeling and how we can think of different sequence models before we're going into the concrete example. And so when we talk about NLP, it's not just NLP, it's also other varieties as well, but particularly NLP, we have lots of sequential data. And just to give some examples, we could talk about words or tokens within sentences. We could talk about characters within words. We could talk about sentences in a discourse or a document or a book or something like that, et cetera, et cetera. And another really important thing about NLP is that there's lots of long distance dependencies where, the interpretation of one word in a sentence might depend a lot on the other ones. If you want to talk about language modeling, there are things like agreement in number and genders. So he does not have very much confidence in himself. She does not have very much confidence in herself. You kind of depending on the word that happened way back at the beginning of the sentence, you have something change in the end. This is a rare example of the necessity of gender agreement in English. It's not actually that common that you have to worry about gender agreement in English, but there's lots of other languages with richer conjugation than English where you need to kind of be careful about this. Another example is something called selectional preference. This is a more semantic thing, which is like, for example, if you're talking about a rain, in one sense, that would be, royalty here. If you're talking about rain in another sense, it would be clouds here. And, this can go as deep as, the various semantic distinctions you want to make it go. So, like, for example, the bird the bird traveled to its nest by flying seems reasonable, but the penguin traveled to its nest by flying seems less reasonable, right? So this becomes very difficult to get everything coherent. So this is a very famous example in English or in NLP in general. I think some people might be familiar with this. But let's say the trophy would not fit in the brown suitcase because it was too big. What does it refer to here? Yeah, trophy, exactly. What about the trophy would not fit in the brown suitcase because it was too small? Suitcase, right. What's the name for this kind of problem? Does anybody know the trade name for this? Co-reference resolution is the task that we're solving, but there's a specific thing for these kind of like pairs of questions. Any ideas? I heard a couple things, but actually Zoom, the guy on Zoom got it correct, it's called a Winograd schema. And a Winograd schema is basically these kinds of pairs of sentences where you change one word and then suddenly kind of like a reference changes or the answer changes. And I think this is a really good way of testing the abilities of NLP models because basically like there's very little way to cheat on these. Like both of the answers are possible answers depending on whether you flip one word into sentence. Let me give an alternative way that you could test this. Let's say the elephant was very, is it big or small? Okay, and like the trophy or the mouse was very small, right? And you don't even need to like do any interpretation of the sentence. You can just look at the correspondence between like elephant and big and mouse and small and answer the question. And so because of this, this kind of like paired way of doing things makes it kind of less easy to cheat on this, on these tests. So, okay, yeah.
Constructing it the other way also, like if they were all using
You could do something like that. I think basically it depends on the type of knowledge you want to test. So like compared to bacteria, mice tend to be, compared to elephants, mice tend to be, would be another example like this. And then you're like comparing, you have turned it into something where you need to compare the relative size of two things. And actually language models are really bad at these things. Like there was a paper called Olympics or something like that, like Olympics, that created some like relative size comparison things. And it turns out that even strong language models were pretty bad at these. So like one thing that you should know is that models tend to be really good at picking up on like spurious correlations, or maybe not spurious correlations, but correlations between like one word and another word, co-occurrence relations and stuff like this. And so turning it into a thing where you can't just easily solve things through co-occurrence relations is hard. And actually, I think the elephant and mouse example is a particularly good one because you add elephant, which is a big thing, but then the answer becomes small. So that makes like the problem even harder. So, cool. Any other questions? Yeah. The what reference? Sorry. Oh, okay. Oh, I actually hadn't heard that news. These slides are 4 years old, so it had nothing to do with that, but very, very timely. Okay, yeah, the timely or untimely, may she rest in peace. Okay, types of sequential prediction problems. So the types of prediction, binary, multi-class, structured prediction. So this is an important distinction that you can be making when you're talking about problems you want to solve. We talked about binary and multi-class classification problems before. So here we have like, I hate this movie, and you want to decide whether that's positive or negative. It's negative. We have multiple classes, so multi-class classification. You have I hate this movie, and then you have 5 choices, and you want to decide between them. Practically, model-wise, you know, these would be very similar models, very similar inference algorithms. Only difference maybe being that you use a sigmoid or a softmax at your very final layer. However, many or most of the interesting problems that we handle in NLP are actually structured prediction problems. And structured prediction problems are things where we don't have a finite number of labels, or if we have a finite number of labels, it's a very large number of labels. And to give some examples of this, we have I hate this movie, and then we're trying to predict the parts of speech of each of the words here. Or we have I hate this movie, and we're trying to translate it into another language. And so for the first one, let's say we have 30. Let's say we have 30 parts of speech in English. How many possible labels would there be for this sentence? You don't need to give me an actual number. Yeah. 30 to the power of 4, right? Because each of the potential words, or each of the words here has 30 potential answers. So that's a very large number. There's no way you could just enumerate all of these and do a softmax for them, right? And even if you could do that, it doesn't seem very prudent to train like completely independent parameters for like PRP, VBP, DT, NN, and PRP, VBP, DT, like NNP, and NNP is like a plural noun. You know, those share structure in some way, so they should be treated together. What about the second one? How many possible answers are there for that? Translation. Number of words in Japanese. So let's say there's 30,000 words in Japanese. And then how many? There's no way of knowing because you don't know the output length. So it is it's highly unlikely, but still nonetheless possible that you could have, you know, a 500-word sentence be a translation of a 4-word sentence. Yeah, it's not going to happen much, but you don't have any guarantee for the length, so you can't even really say. Okay. So these are different types of prediction. Yes, sorry, I got a question about whether I can repeat the live question, audience question for the Zoom audience, and I'll try to do that starting next time. Types of prediction, we have unconditioned versus conditioned prediction. And we talked about this before. So unconditioned prediction is basically where we're just predicting the likelihood of an output. Conditioned prediction is where we're predicting the probability of an output variable given an input. Now, types of unconditioned prediction. How can we model unconditioned sequence prediction? So the most popular way of doing this, as I mentioned before, is left to right prediction, like what language models typically do. And so basically what they do is, let's say we have 4, let's say we're just modeling a sentence. The first thing we do here is we predict the first word, then we predict the second word, then we predict the third word, then we predict the fourth word. And so essentially what that does is that reduces a space of, 3,000 to the potentially infinite, but let's say here it's 5, because we need to predict the 4 words and then the end of sentence symbol to make the final decision. And so it's taking this very, very large space and basically turning it into 30,000, but we do it 5 times. We do the 5 multi-class classification problems. And so the computational complexity of doing something like this, assuming we pick a single output at each time step, it becomes much simpler. And when we're training the model, if we're conditioning the model on the previous words in the sentence, so like when we predict, I hate this movie, and we want to train the model to predict movie next, then if we just assume the previous words are I hate in this, then again, we only need to enumerate the vocabulary. We don't need to expand all the possible choices. Is this clear? Yeah, how is this unconditioned? So that's a very good question. It's not conditioned on anything other than the data we're modeling. Is maybe a more appropriate way to say this. So we're modeling X. X consists of X1 to X length of X, and because we're predicting the first variable here, given nothing. Basically, we have no conditioning. We have no conditioning for the prediction of the sequence. So. Yeah, it's a joint of like X1, X2, X3, X4, X5, and X6. Yeah, excellent for that. So good question. The question was, doesn't it assume some amount of independence if we're just multiplying them together? It's not assuming any independence because we're always conditioning on the previous ones. Yeah, so yeah. However, that's what we're going to talk about next, actually. So this one is not, this is not assuming any independence. It's conditioning on all the previous, elements that we generated, be they tokens or words or characters or whatever. One example of this here, which we haven't covered yet, but we're going to cover this time, would be an RNN-based language model, recurrent neural network-based language model, or a transformer-based language model. These would all be examples of this variety of prediction here. There's also, the next thing I'm going to talk about is a left to right Markov chain. And what this means, what a Markov chain means is basically, at some point, we start ignoring the older context. We start ignoring the context that we have seen a long time ago. So first, we predict the first word based on null, like this. Then we predict the second word based on the first word. We predict the third word based on the first and second words. But when we predict the fourth word, we assume independence from the first word and only use the second and third one. So this would be a order n-1 Markov chain. So it's basically a Markov chain of length of order 2. So what would be an example of something like this that we talked about already in class? Yeah, an n-gram language model would be an example of something like this. So yeah. Another example, an n-gram account-based n-gram language model would be one example. A feed-forward neural network language model would be another example. Because if you remember our feed-forward neural network language model, we put in the previous 2 tokens and looked up embedding string. We also have independent prediction. So independent prediction is when we're not, when we're predicting each output independently. And basically what that's doing is that's saying, look, I know there's an interaction between these parts of speech. I know there's an interaction between these words in the output sentence, but I'm going to ignore that and just not model it whatsoever. And because of that, you know, your model becomes simpler, but you also like lose out on modeling the interactions between them. So any idea of, yeah. Does this sort of mimic naive Bayes? I mean, naive Bayes is basically a unigram language model. So yes, I guess so. Because you can see the formula is the same as naive Bayes. The only difference between a naive Bayes sentence classifier is the naive Bayes sentence classifier actually was conditioned on the label. So yeah, it's maybe more like a unigram language model, which is actually the answer here. But another example of this, let's see. So another example of this could be something like a part of speech tagger that predicts each part of speech independently. There's also something called non-auto-regressive translation, which is basically translation that predicts each word independently after running it through like lots and lots of neural network layers. These are also examples of independent prediction, but I'll be covering them later. So the final example is bidirectional prediction of the output. So bidirectional prediction of the output, basically you're conditioning the prediction of each output here based on both the left and right context. So what you're doing is you're predicting the value here conditioned on all the other values. So this is, I was going to do a quiz, but I accidentally put it on the screen, so I figure I gave away the quiz. But there's something here called like masked language models, or masked word predictors. They're used very widely in pre-training models like BERT or other things like this. However, despite the fact that they're called masked language models, they're not actually really language models by the strict definition, because the definition of a language model is something that predicts the probability distribution over language, over an input, linguistic input X. But it's not the case that you can just predict like this based on all the right context, this based on the left and right context, et cetera, and still get something that's equivalent to the actual probability, because that's not how the chain rule of probability works. The joint probability is the probability. You can go in any order. You can go left to right, you can go right to left, but you can't predict a word based on a word that you haven't predicted yet. So here you haven't predicted the right words before you predict the left word. So it's a little bit of a misnomer, but I'm not going to avoid saying masked language model anyway, because everybody says it and it's kind of like, standard. So I'll say that, but you can think in your mind, this is maybe not actually a language model. Yeah.
Isn't this just like
is this like word2vec? Yeah, that's also what word2vec is doing. So I'm going to talk about this a little bit more in the pre-training lecture, but basically what you do in pre-training is you set up some sort of prediction problem. It doesn't actually have to be a language modeling problem. It can just be a prediction problem. And from the prediction problem, you learn representations. And that's the case for Word2Vec, BERT, you know, just about anything else. Recently, left to right models like GPT-3 or Bloom or OPT or other things like this that you probably have heard of have become a lot more popular. And now people are focusing back more on these left to right models, but things like BERT, Roberta, other things like this use this framework down here, and Word2Vec. Yeah. Yeah, so Word2Vec, the question was, does Word2Vec have a left window and a right window, and you predict based on that? For Word2Vec, yes, that was the case. For the more modern models, that's not the case. They just use the entire input. Okay, cool. Yeah, very good questions, yes. Okay, so that's a good question. Is there any reason why we think this pre-training task works well for downstream classification at all? I got the same question last time, and I said I was going to defer it until we talk about pre-training, but I guess I won't do that because you know, so many people are wondering. My idea of why pre-training to predict the words in text works so well is basically because in order to predict the words in text, you need to know a lot of other things. Like, for example, I gave some various examples before about like these Winograd schemas here. And in order to predict, like, for example, that there was a trophy here. There was a trophy that followed this, you know, sentence here. You'd need to basically understand the sentence. You need to know that trophies are bigger than to go in suitcases and other stuff like this. That's maybe not the best example. Here's another example. In order to predict whether the difference between here is himself or herself, you need to know that there's gender agreement between these two things. And so in order to know there's gender agreement between these words, you also need to know the gender of the words. Another example, like he being followed by a stereotypically male name or she being followed by a stereotypically female name is also something you need to do do language modeling well. So you also kind of need to know the stereotypical gender of names associated with names and other things like this. So basically, in order to predict the words that appear in a sentence, you need to know a whole bunch of different things. Another very interesting finding recently is that there's a lot of data on the internet that's basically solving exactly the problems you want to be solving. So, for example, just to think about sentiment classification, there's a ton of reviews that say 5 stars, and then they have the review, right? And then to predict the 5 stars, you need to know whether the review is positive or negative. So, like, the text that appears on the internet is like pseudo-supervised training data for a lot of these tasks. So, yeah.
Can you also make this analogy with, like, teaching a child some language and not to know the language by way of understanding how context works? They can sort of do tasks like in the blank or question answering or any other thing.
Yeah, so the question was, is there an analogy to teaching a child language and how, like, once we teach a child language, they can do other things like filling in the blanks and stuff like this? Maybe yes. There's very interesting differences between how children learn language and like large language models learn language. So I wouldn't say they're exactly analogous, but maybe a little bit. Yeah. Children learn language by interacting with the world. They form a very strong world model before they even start learning language. And yeah, I have a daughter, so I love talking about her, and I'll tell you more if you're interested, but maybe not during the class. Okay, so now I'd like to go to condition prediction. And when I say condition prediction, it's not that every prediction we make is not conditioned on something. It's rather that the variables we're interested in predicting are conditioned on some variables that we're not interested in predicting or we're not going to worry about predicting. So an example of this might be something like translation, where the input is your source language, the output is your target language. The most common way of doing this prediction is essentially you have an input text here, and then you calculate the output text conditioned on the input text and all the previous words in the output text. So it looks like this essentially. These are like sequence models. We're going to be talking about them more later. There's also non-autoregressive condition prediction. And basically what this is like what I mentioned before, it's calculating all of the output variables independently of each other. So it's not they're all conditioning on all of the input, but none of the output is conditioning on each other. And so some examples of this would be a sequence labeling task where you make all of your predictions independently of any of the other predictions. So you feed your sentence through BERT or whatever else you want to feed it through, and then you make each prediction individually. And then there's also things like non-autoregressive machine translation. Okay, yes. Yeah, I'll give some examples in later slides. I have another question. Is scalability also one of the reasons why mass language models work so well? The self-supervised setup means we have theoretically infinite data, and the only challenges are compute and data quality to some extent. So I would say that's a complicated question, which I will mostly defer to the pre-training discussion. But scalability is very important if you're training these models. I also think that's the main reason why transformers have taken over recurrent neural networks. It's not the case that like transformers and self-attentional models, which again we'll cover in later class, are like way better when you scale them up. They seem to be relatively similar, but they're rather like way faster to compute, especially in parallels. So I think that's one of the big reasons. So what are Y and X here is another question from Zoom. And here, Y is anything you want to predict, and X is anything that you're using to predict it. Just to give a few examples. X could be the input side, the left side of anything here, and Y could be the output side of anything here. But because we're talking about sequence prediction, it would usually be something like this part of speech sequence or this sequence here, this Japanese sequence here. Notably, language models can also be used for condition prediction. Like if you give it a sentence and then ask it to continue the sentence, like a prompt in some way. And we're also going to talk about more methods to do that later. Any other questions? Okay, I got another question, which is where would feature extraction plus a conditional random field fit here? So a feature extraction plus a conditional random field, which I'm actually not going to talk about anymore. I would have definitely talked about it 3 or 4 years ago, but they're just not widely enough used to go into all the detail we need to go into. But a conditional random field is basically a graphical model that doesn't do prediction of. It's similar to the bidirectional prediction here, but instead of doing prediction of a single element given all of the others, it just has an effective way to calculate the probability of all of the variables at the same time. It has an effective way to calculate the joint probability of all of the variables. So it's kind of like one big red box. You're predicting it all at the same time. And the way you're able to do that is through dynamic programming. So you don't actually have to enumerate all. You don't have to be. The way it does it is through some independence assumptions and dynamic programming, so you don't have to enumerate all of these outputs, but you can calculate the maximum. lots of questions. Can we tie back these methods to the types of problems we solve? Text classification, machine translation. Basically, are there any preferred methods for a type of problem we solve? Super good question, and the answer is definitely yes. So the more interaction there is between the output variables, the more you need to worry about modeling the conditional assumptions between them. So the model up top here allows you to consider the interactions between the output variables. One place where this is very, very important is machine translation. And the reason why it's very, very important in machine translation is because there's many different ways to translate something. So if you kind of like arbitrarily choose the first word, like just to give an example, let's say we want to translate a sentence to the dogs bark, or translate a sentence that has the meaning the dogs bark. You could also translate it as dogs bark, right? And if you say, if the dogs bark and dogs bark are both like equally likely, and you predict each of the words independently, you very well might get dogs, dogs bark, or maybe dogs, dogs, or something like this, because this is like an end of sentence symbol here. So if you don't consider the interaction between the output variable, you're going to have lots of trouble. Sure, there are tricky ways around this. There's things like non-autoregressive translation, which we won't cover in detail, but it is a thing that exists. But it's really hard to get MT to work. On the other hand, there are some things that are relatively easy to get to work. So what is an example of something where you can just predict all of the outputs independently? Maybe it's something that somebody in the class has done before. Like you take BERT, just have independent classifiers on each token. Yeah, I've heard part of speech, NER. Yeah, these are good examples. So part of speech tagging, named entity recognition are some examples. Yeah, I see part of speech tagging. And the reason why these ones are kind of okay is because there's not a whole lot of possibilities. Like in most cases, there's only really one possibility for what named entity anything could be. There's not multiple interpretations. There are some examples. So if you say time flies like an arrow, you can enumerate all of the parts of speech and see that there's like 4 or 5 different like potential part of speech sequences, but that's much more rare than just having one like reasonable part of speech sequence for the entire thing. And in those cases, this actually works pretty well if you have a sufficiently strong feature extractor. Yeah. I have an example of that later, so that's another good. So maybe I'll go on to that. How is the length of the sequence controlled in non-autoregressive translation? That's another really good question. Usually you predict the length first, or you predict several lengths first, and then you generate for that length. But okay. Thank you for all the questions, but I'm going to stop it here so we actually move on past slide number 6. So okay, moving on to the basic paradigm. We have extract features and predict. And the way extract features and predict works is basically given an input text X, we extract features H from that input text and then predict the labels from it. And there's kind of two major paradigms that I'm going to talk about this time, and they also a very large number of tasks fall within these two paradigms. One is text classification or sequence classification. And basically here, we take the input, we run a feature extractor, and we get one vector for the entire sequence. And from that, we make a prediction. The alternative is sequence labeling or sequence modeling, where we take in the input and we get a vector for each token, and then we use that in some way to make independent predictions or feed it into something we use downstream. And very often we can use the same feature extractor for both of these tasks, but it's an important distinction. Okay, so in particular, I want to talk a little bit about sequence labeling tasks. And sequence labeling, as I said, is very broad. It covers a very broad variety of tasks. So this is just to let you recognize when you have one of those tasks. So given an input text X, we want to predict an output label sequence Y, and it generally has to be of equal length to the input sequence. So this is a feature of sequence labeling. So we have part of speech tagging, be one example, input part of speech. Lemmatization might be another example. So lemmatization is predicting the root word for a word here. And because each word has exactly one root word, this would be another example of sequence labeling. In contrast to part of speech tagging, it has a very large label set because the label set is the number of lemmas that you have in the language, but nonetheless, it's a sequence labeling task. Another example is morphological tagging. So this is basically coming up with morphological features of each word. And here, you kind of have some structure in the output labels. So you can have like tense, you can have verb form, you can have the number type, etc. But it's still a sequence labeling task because you have one label for each word. I'm making a distinction also with span labeling here. And the reason why I'm making it, many people don't make the distinction, but I'm going to make the distinction, which is given an input text X, we predict an output spans in labels Y. And one example would be named entity recognition, which is where you're recognizing spans and you're recognizing the type of the entity in the span. So this would be a person and this would be an organization. There's also syntactic chunking, which identifies that this is a noun phrase, this is a verb phrase, this is a noun phrase. Semantic role labeling. And what this does is this identifies predicates in here, and it also identifies the semantic roles, like what role is this playing with respect to predicates. So this is also very broad. You can frame a lot of different things this way. The reason why I treated this as different than sequence labeling is because you can also come up with methods that, for example, learn span representations. They take all the words in the span and combine that into a representation and use them differently. So I think it is worth thinking of them differently. However, any span labeling problem can be translated into a regular sequence labeling problem. So one way you can do this is you can predict beginning, in, and out tags, BIO tags for each word in a span. So you take this sequence, or you take these set of spans and turn it into a sequence that looks like this, where this tag indicates the beginning of a span, in a span, outside of a span, etc. And then you can deterministically translate this back into the spans that you actually want. Okay. Any questions? Okay, don't see any on Zoom. Okay, so I'm going to talk about one sequence model, and these are recurrent neural networks. Recurrent neural networks are a relatively straightforward extension to essentially a feed-forward network that allow you to nonetheless model sequences of arbitrary length. And recurrent neural networks were kind of popularized in the early 1990s or late 1980s as tools to remember information. And basically the way a feed-forward neural network works is you have some context, you feed it into a network, transform to get hidden states, and then you make your prediction based on the, to get features, and then you make the prediction based on the features. The difference between this and a recurrent neural network is that the transform of the input context is also conditioned on the previously calculated hidden states in some way, or features in some way. So what does this look like? Basically, we have an initial hidden state. Oh, sorry, I missed a question on Zoom. And sorry, I actually missed when it was asked. But what the question is, what is a span in this context? And basically a span is any sequence of words greater than or equal to 1. So like Graham Neubig is a span. Graham Neubig is also a span. So that would be any span. Also, Carnegie is a span because it's a linked one span. Okay. So going back to RNNs, this is what they look like when you actually apply an RNN to an input sequence. And so you notice here that we're extracting context. So we're taking I and converting it into a word embedding. And then we essentially have our initial state. This initial state might be all zeros, or it might be something that we learn. Either way, it's just something that we start out the sentence with. And from this, we run it through this RNN that takes in the context in the previous hidden state and predicts the label. And then you can further use this to predict the label. And then you can continue doing these steps where this RNN is now conditioned on the hidden state after reading the first word, like this. And now the nice thing here is that when you're talking about predicting the label of movie, now this hidden state has been conditioned on I and hate and this and movie. So basically it's seen the entirety of the input sentence. So because of this, it can condition on infinite previous context, which makes it very appropriate for handling this sort of modeling here, right? Because we want to condition on infinite previous context. The neural network has been able to see infinite previous context. Any questions there? Okay. Yeah.
Is there also a way to figure out, I mean, for example, say the predicting at all points, if we want to have one prediction for every sequence, is there also a way to find at what point do I have the maximum or the best context to do it?
Okay, really good question. So like, let's say the question is, let's say we want to make a prediction for the whole sentence. Which context should we be using? What is the what is a straightforward answer to this? Yeah. The last one. Good idea, but bad idea. So I will tell you why it's a bad idea in a second after we talk a little bit more. So when we train RNNs, one way we train them is if we're making predictions at each time step. Let's ignore the setting of where we're not making predictions until the final time step for now. If we're making predictions at each time step, basically what we do is we have a label. And for each time step, we calculate a loss. And given this loss, we then do backpropagation. But how do we do backpropagation? If you remember, we had to do in order to do backpropagation, we basically needed a final single node in our neural network that we use as our initial state of backpropagation. The answer here is simple. We just add them all together, and now we have one node. So we have one node that we can backprop from. I got a comment that we do backpropagation through both layers and times. That is true, but we're right now we're talking about a single layer RNN. So if we added more layers, we would have to backprop through layers. So now we have a directed acyclic graph that ends in a single value here, and so that gives us our total loss, and then we just backprop through it. So we backprop through this total loss. Yeah, we backprop through this total loss, and then it just flows back through our graph and allows us to calculate the value of all of the parameters. One important thing to note is that the parameters are tied across time. We use the same parameters for every time step. So you'll notice here I have this RNN function. Within this RNN function, we have parameters, and those parameters are reused. We use the same ones at every time step. And because of this, the derivatives that flow into this this RNN function, this RNN function, this RNN function, and this RNN function all flow back into the parameters that are used in calculating these functions. Actually, I just realized I don't have the actual equation of the RNN on these slides. I have an equation on a later slide when we talk about variance of RNNs. But basically, the way the RNN works is h 20 minus 1. This is the most common one. So basically what this is doing is we talked about how like traditional feed-forward neural networks use, traditional feed-forward neural networks would basically be like this. They have wx times x plus b, and you run it through any nonlinearity like the tanh. But recurrent neural networks additionally have another parameter matrix that conditions based on the previous time step. And hopefully that's also visible on Zoom. Okay. So one thing to note here is that be in a second. One thing to note here is I'm talking about RNNs here, but actually this is exactly the same for convolutional neural networks, transformers, any other sequence modeling thing that we use in NLP. The basic idea that we use the same parameters to calculate across different time steps is really important because it allows you to handle arbitrarily linked sequences. If we had different parameters for the first time step, second, third, fourth, all the way up to 60th, then suddenly we wouldn't be able to model sequences of length longer than 61. And also the training data that went into them, might be very heavily dependent on like what time step we were modeling. Yeah, I had a question.
While backpropagating the loss, is it the transfer equally to each time step then? How exactly does it backpropagate?
So while backpropagating the loss, does it transfer equally to each time step? And that's a very good question. I'll get to that in a second too. So before I do that, I'd like to talk about the application of RNNs. So what can RNNs do? They can represent sentences by reading whole sentences and making a prediction. You can also represent a context within a sentence to read the context up until that point. So when you encode sentences, one very common way to do things is to do exactly what was said before, is the answer to what we do when we want to encode a sentence. We just use the final one here. And it makes sense to use the final one in some way because the final one is the only embedding that has access to all of the words in the sentence. So that makes sense. But there's a big problem with that I'll be talking about in a second. These can be used for, sentence classification. They can be used as text classification, retrieval, comparison between texts, etc. Contexts, which I've talked about before, this can be done for sequence labeling, calculating representations for parsing, machine translation, any other things like this. Also language modeling. Okay. So we had a question about bidirectional RNNs earlier, and that is basically the architecture we have up here. A bidirectional RNN, what it does is it runs an RNN not just from the left to right, but also from the right to left. And why would we want to do this? Let's say we're trying to handle something like sequence labeling. If we only use a left to right RNN, when making the prediction for the first word, it's only going to have access to information before that word, like that word or information before that word. And that seems like a problem because, the part of speech of a word might be determined by the following words, not just the previous words. So what we do here is we then concatenate these together and make a prediction. And so now every single vector that we have here is useful for making a prediction for each of the words. So this is a very common thing to do as well. As I mentioned, these could be used for language modeling. What does it look like for language modeling? So what we essentially do is we feed in the previous, we feed in like a sentence start or end symbol. We run this through the RNN. We predict the first word in the sequence. Then we take this word, we feed it in, we predict the next word. And we go like this all the way to the end where we have like a sentence end symbol, essentially. So another way you can think of this, is basically we have shifted we have shifted the sentence one time step to the right, shifted the sequence one time step to the right, appended a sentence beginning signal to that, and then we take the original sentence, append the sentence end symbol to that, and then use this to do regular sequence labeling. So this is essentially, you can see language modeling is essentially sequence labeling if you look at it that way as well. It's just sequence labeling over like shifted sequences. And that's a convenient thing to know if you want to kind of be implementing this. It's how it's internally implemented in a lot of places. So. So the first one is always the start tag.
Yeah, I mean, how does it predict I?
How does it predict I? Not very well is the answer. But basically, you're conditioning the prediction of the first word in the sentence on nothing. So the best thing you can possibly do is have essentially the distribution over all possible first words in the sentence and try to model that as well as you can. So the word I or the word the is more likely to appear in the first position than a random verb, for example. So it does give you a little bit of information that, hey, this is the first word in the sentence, so you should predict what the first word in the sentence, but it's not very informative. And actually, when you're doing language modeling, you'll find the great majority of the log likelihood or the log loss of the sentence comes from the first token. I wouldn't say the majority, but a lot of the log loss of the sentence comes from predicting the first token. And then after that, now you have some context with which you can get a remainder. I see at least one. Oh, you were just, okay, yeah. Okay, for language modeling? Okay, what happens when you use a bidirectional RNN for language modeling? This is a good question, a little bit of a tricky answer. Then it's not language modeling, yeah. So if we go back, so good answer. If we go back to what I was talking about before, we can't condition language models on bidirectional context. So you essentially, you have no way of preventing a bidirectional RNN from doing that unless you train the two models separately. You can train a model from left to right and then train another model from right to left, but those are two language models. It's not one language model essentially. Interestingly, that was used very shortly in a very popular model called Elmo. They basically pre-trained one language model from left to right and another language model from right to left to learn representations, but we don't do that as much anymore. Okay. Any questions? Okay, great. Okay, so let's go back to the question that we had before. Which is why is it a bad idea to be learning a text classifier by using the final representation in the sentence? And the answer is this: vanishing gradients. Vanishing gradients are not exclusive to RNNs. They're a really big problem in a lot of different models. And actually, if you're going to do any sort of model architecture engineering, the model architecture engineering, a lot of it is probably going to be in some way to avoid vanishing gradients and to make your model train better and more appropriately. So it's an important thing to know. So basically what happens with vanishing gradients is every time you do backpropagation through almost any function, it changes the gradients in some way. I mean, it's kind of obvious, right? You know, like, there's a reason why we have the function. It's changing the inputs to outputs, but that also means it's changing the gradients. And in particular, if we think about a function, like let's say we're talking about the tan-h function over here. Does anyone have an idea of what the gradient of the tan-h function looks like? Just a description is fine. It goes to 0 at the end. It's like a little bump. So this is like, so the tan-h function goes from 0 to 1, -1, and it crosses zero at 0. And then the gradient looks a little bit like this. There's this bump. There's this bump at 0, and then on either side, the gradient becomes 0. So especially if you're running it through something like the tan H function, if you get an input on either side here, basically your gradient completely disappears. It turns into 0, and you lose all information flowing back through that node in the neural network. And because of this, tan H is particularly bad, but basically any function, there's only one function that doesn't change your gradients in any way. And I'll let you think about what that is. But if you have any function that changes your gradients, by definition, it kind of makes them larger or smaller. And a lot of functions like the tan H tend to make them smaller. And if that's the case, basically you have a loss here, and you're back propagating through a bunch of time steps, and your gradient gets smaller and smaller and smaller. And because your gradient gets smaller and smaller and smaller, the representations from the very first part of the sentence kind of get very little gradient, don't get learned, and you don't learn the connection between the stuff at the first part of the sentence and the final decision that you're making. This is also true for language modeling. So if you're using a straight up RNN, it becomes very hard for that to condition over long context, and it learns only to model very local context and doesn't become a very good model. Yeah. Yeah. Yeah, so very, very good question. The question was, if we are aggregating over every time step, wouldn't we have a problem where it aggregates over, where we have more gradient on the earlier tokens? And kind of yes and no. Before I talk about that very quickly, let me also talk about exploding gradients. And exploding gradients are the opposite problem. So let's say you said, well, I don't like vanishing gradients, so I'm just gonna make, a function where the gradient is never less than 1. It's 0, it's 1, but then it gets bigger and bigger and bigger, which also isn't very hard to make. X cubed is an example of a function like that. Or, x cubed plus x is a function like that. And however, that's also a problem because now your gradients get bigger and bigger and bigger. The gradients at the very beginning of the sentence wash everything else out, and you get training instability and stuff. So there's only one function that fixes this problem. What function doesn't change your gradients? The identity function. Yeah. So, however, the problem with an identity function is that in order for neural networks to learn anything, they need to have a nonlinearity. They need to have something that has some sort of nonlinear adjustment to the representation. So identity doesn't satisfy that. That doesn't work. So yeah. Would something like the leaky ReLU handle this well? So the leaky ReLU is, it looks a little bit like this. So here, I don't remember the common constant, but it's 0. If the input value is less than 0, it's 0.1, and then here it's 1. What do you think? Yeah, it will still vanish if the input value is negative. So, and now you do that over and over and over again, and your gradients are going to get less. So, basically, there's no way around this. Every function makes modifications to your gradients, and if those modifications are too big or too small or bad in any other way, then you're stuck. Okay, so this is really important. They're squashed by nonlinearities or small weights and matrices. Now, let me go back to this, which was a very good question. Let's say we're aggregating over all of these. Would it be the case that the ones here get more gradient than anywhere else? The answer is yes, but the problem is they might not be getting enough of the gradients from long distances away. So they will be getting lots of gradient from here, but they'll be getting much less gradient from here because the gradient from here has already gone through many nonlinearities. So basically it would be able to learn, local tagging information, but it'd have a lot less, it'd have a lot of trouble learning global information. Okay, so there's actually a relatively simple fix for this for text classification. Let's say we're just talking about text classification. What's a better idea than taking the last representation? Yeah, get all of them, aggregate them all together. So this is a method called pooling. Basically, you take a whole bunch of representations and you run them through some function that allows you to turn a whole bunch of representations into one. You can take the maximum, that's called max pooling. You can take the sum or the average, which are called like sum pooling or mean pooling. And even if you're using an RNN, it's still probably a better idea to use those pooling functions to battle with vanishing gradients when you're doing classification. And that's actually also the case for any other model you want to be using. Very often for transformer models, it's still better to do max pooling or mean pooling when you're doing classification. Okay. So in recurrent neural networks, how do we fix this problem? There's a very clever fix to this, and it has to do with the identity function. It's the only function we can possibly use to prevent vanishing gradients. And there's a method called long short-term memory, which basically incorporates the identity function in the model itself to try to mitigate this, this problem. And basically, the basic idea is to make additive connections between time steps, because addition or the identity across time steps doesn't make a difference or it doesn't diminish the gradient. And then there are gates to control information flow. So this is what it looks like. It basically has two hidden states. One hidden state is called the memory cell, which is why it's abbreviated C. Another hidden state is called is like the normal hidden state, so that's called H. And it basically has three gates involved. One is the update gate, which decides whether we make like what value we update. We have the input, this is the update function. So it decides whether we make a positive or negative change to the memory cell. We have the input gate, which basically decides whether or not we make a change to the input cell. And these, there's an element-wise multiplication here. And then we add any change into this memory cell. And then we take the memory cell, we run it through a tanh here to kind of squash it down to a reasonable range. And then we have an element-wise addition over this output gate. In later versions of the LSTM also added a forget gate that allows you to forget some of the information in the memory cell. But if you add the forget gate, it becomes a little bit more complicated, like this additive relationship no longer holds. But the most important thing you can see is basically there's an identity relation between the previous memory cell and the next one. So that allows you to take information over time. This additive relationship is really, really important in any sort of neural network nowadays. It's also included in transformer models in the form of something called residual connections, which basically add the input of a layer to the output of a layer. And that also prevents vanishing gradient, except instead of over time steps, it's over the layers that you use. So this is a really important concept to know if you want to train your models. Any questions about this? Yes. Could we add skip connections? So yes, basically you can almost view the memory cell as having a skip connection because it's additive. Like another way you could view this is so basically you could view the addition there is kind of essentially a skip connection that goes like over the LSTM box. So that's essentially what's happening. I have another question on Zoom. In a bidirectional RNN or LSTM, the network traversing from right to left experiences a sequence of words in an opposite order, which isn't really English. So how does it add any value to the language model? So that's a really good question. So I mentioned before that left to right and right to left are not actually as important in language. There's lots of languages that write from right to left. There's also a lot of languages that write from top to bottom, like Chinese and Japanese traditionally were written from top to bottom. So left to right is not important. However, past to future is, because we all speak and we all speak from the past to the future. So there is kind of a natural ordering of language. And for example, it's much more common to have a verb at the end of the sentence than a beginning. Or if you have the verb at the end of the sentence, then like the grammatical properties change. So there is a very natural ordering of language, and right to left LSTMs kind of violate that. They read in the opposite direction. However, there's a lot of things. I think also humans are resolving ambiguity based on things that they heard previously, because they have the ability to go back and think and reinterpret things, right? We're not just machines that read something in once and then don't think about it anymore. So I think the right to left LSTM is providing necessary context from the later words to help disambiguate the earlier words. Great. Okay, so finally, we're getting near the end of the class. I'd like to talk about actually training these sequence models. Yeah, sorry, go ahead. C and H, so C stands for memory cell. So the cell and memory cell. H stands for hidden state. And H, the hidden state H is used in RNNs and everything else. C is kind of specific. Okay, so for efficiency tricks for sequence modeling, I have to apologize. Actually, I realized that I removed one lecture and it was missing the thing on mini batching. But mini batching, basically the idea here is when we are training neural networks, we want to process multiple examples at one time. And the reason why we want to process multiple examples at one time is because any hardware you're using, be it CPUs, GPUs, or TPUs, or anything else, they're much better at processing lots of operations at once than if you write like a Python for loop and do all of the operations independently. And so because of this, we want to group together like processing of multiple sentences at the same time, especially when we're training our models. And in feed-forward networks, there's a really simple way to do this. Basically, what you do is you take a whole bunch of examples. Like, let's say we have our input 1, input 2. And these are just completely different training examples, like your first input, your second input, your third input, your fourth input. And instead of running all of these through your network separately in a for loop, what you do is you concatenate them into a matrix and process this matrix all at once using your GPU or whatever. So this is a very standard trick for training neural networks. However, it's a little bit harder when you're handling sequences. And there's a couple reasons why. One is that within sentences, we no longer can make assumptions about the inputs and outputs being independent. So we can't, like, for example, take the first word in the sentence and the second word in the sentence and just stick them all together, because calculating the representation for the second word in the sentence relies on the first word in the sentence. So we can't just go ahead and do that. Another problem is that sequences are of various lengths. So we might have sentences that are 20 words and 17 words and other things like that. So the way we handle this is using something called padding and masking. And essentially the way padding works is we add an extra sequence. This could be like a mask symbol. Also, it doesn't need to be the end of sentence symbol. And we do a loss calculation. And now, because all of these are essentially the same length, we can just calculate them like they're, identically sized examples. And then we do some sort of masking where what the masking does is it basically multiplies the loss functions or whatever else we calculate by 1 or 0. And so that removes any loss we might have gotten from making a prediction on this like non-existent token. And we take the sum of them. However, if we do this in a naive way, this will not be any more efficient and it might even be worse. And the reason why is like, let's say we have a really, really long sentence, 300 tokens, and then we have some other sentences where most of them are 5 tokens. Now, the great majority of the tokens in this batch are going to be pads and masks that we wouldn't have had to calculate for these 5-word sentences. And so because of this, it's very common to essentially sort sentences and bucket them in different length buckets. So like, you know, all of the sentences that are length 5, all of the sentences that are length 6. And then when you get up more and you start running out of sentences of the appropriate length, you get like all sentences of length 20, 25 to 27 or something like that. So now you're doing like a little bit of padding, just a little bit of padding and masking instead of lots and lots. Yeah.
I'm wondering, like, can that introduce like a bias because of IID assumptions?
Can that introduce a bias because of IID assumptions in the training? Excellent question, and yes, it does. It makes each mini batch be a little bit biased. The biggest problem is not that it's actually modifying any underlying assumptions about stochastic gradient descent, because essentially what it's doing is it's just making a rougher IID assumption. It's like not assuming, it's assuming that things in the same bucket, in the same batch are IID, but not like within batches. So if you want to go into the theory, there's more theory about that. But the bigger problem is we use things like stochastic gradient descent. And stochastic gradient descent is very sensitive to like the directions you're moving in. And this can take a very big step in the direction of like all sentences that are length 27. So like length, 27 or length 5 or something like that. So if you think of the extreme, version, which is like, let's say you were training a sentence length classifier, then suddenly your sentence length classifier would get all examples with the same label, and that might throw your training off. So it is a problem, but the benefits you get from doing this tend to be larger than the losses that you get from doing it. So it's very, very frequent. And you might notice, like, if you're using a sequence modeling toolkit like FairSeq or something like that, it just does this internally without you even knowing it. So the reason why I introduce it here is because this is a feature of like lots of training code that you might be using. Another thing that I should mention is you need to fit everything in memory. And so there's a couple ways you can make sure that everything fits in memory. Generally, the amount of memory you're using from a individual batch of data is like correlated with the number of words in the input. And so it's most common to choose the number of sentences you use in a batch so that the number of words is relatively constant across batches. So if you have a batch with lots of short sentences, you might have more sentences. If you have a batch with lots of long sentences, you will have fewer of them. Okay. Final thing, handling long sequences. So sometimes we'd like to capture long-term dependencies over long sequences. I'm going to have a whole class on how we do this later. But for the time being, just knowing the very basics in case you want to implement it yourself. Like, let's say we want to handle full documents, or we want to model text from a Wikipedia article or a book or something like that. This may not fit in memory, especially if you're using GPUs or very large models. So there's a number of ways to do this. The most common way to do this in recurrent neural networks and some varieties of transformer models is something called truncated backpropagation through time. And basically what truncated backpropagation through time does is it calculates one sequence, and then it does backpropagation through this sequence, calculates all the losses that you want to calculate. And then when you do the second sequence, you pass only the state. You remove all of this computation graph from memory, you pass only the state, and then you calculate the next sequence based on the state, here. And the reason why this is still better than nothing, than reinitializing your state, is at least this sentence is able to use information about what you had in the previous sentence, even if that isn't like backpropagated into the sentence here. So this is called truncated backpropagation. Yeah. So I'm assuming that you have training data for the first sentence and the second sentence. So like, let's say we're talking about tagging or sequence classification or language modeling. For all of them, you would have the tagging, language modeling, sequence modeling loss for the first sentence and backprop using that loss. And then for the second sentence, you would calculate the loss. So then this wouldn't backprop. Yeah, good, very good question. So another thing that people often do is kind of multi-scale architectures. This is really popular in speech, for example, because speech has like many frames for each word. So what you do is essentially at the very early layers of a multi-layer network, you calculate on every input, but in the later layers is you concatenate every 2 inputs as input to the layer. So you downscale by 2, then you downscale by 2 more, and that kind of like exponentially decreases the sequence length. So this is a common trick also. Great, so that's all I have. There's 1 more minute left in the class time, so if there's one quick question, I could answer that. Or okay, looks like not. So thank you, everybody.